Hello folks, here's the second part of the video about sequence examples, and we're gonna go over more examples about the sequences. Here's just I can say the first example about the limits, of course. Limit as n goes to infinity. What can we say about 4n plus 5 divided by square root of n plus 3. So now we're looking at the limit of this function, and this is this sequence, and really, I mean, you can really look at the degree of the top. It looks like 1. The degree of the bottom, you have a polynomial here under the radical, so you can just say this is degree 1, and the square root will just make the degree kind of like, it's not the degree, but we may just think of it as 1/2. And the top is degree larger than bottom. We can say this will diverge to infinity. We can expect that. But again, as our previous examples, you can really compute limit x goes to infinity of the corresponding function, which is 4x plus 5 and divided by square root of n plus 3. And you can just see this is an infinity over infinity type limit, and we can use LR, and that will be a limit x goes to infinity. The top will be simply just 4, and at the bottom you can see this is the bottom part. You can really write this as, oh, I'm sorry, that's just x. That's just an x. The bottom part, you can really write that as x plus 3 to the power 1/2. So if you take the derivative of this one, that will be just 1/2 x plus 3 to the power negative 1/2. So basically, you can see you have a negative power at the top of x plus 3, so you flip in, or you can flip, or you can just put this at the top, because this one exactly looks like 1 over square root of x plus 3. So if you really simplify this limit x goes to infinity, I have 1/2 you flip, so that will be 2 times 4 from the top times square root of x plus 3, and you can definitely see that limit is just infinity, because x plus 3 goes to infinity. So this is a divergent sequence. Okay, this is the first example. Now we can now go over the second example, and that will be kind of like a general example that might be used in many parts of the series. This is just, we're going to find limit r to the n when n goes to infinity, where this r is a, so r is a real number, and the question is this, like, for what values of r r to the n is convergent. So that's really the question, and you can really see, like, you have to, we can go for some, for example, certain cases. If you have, for example, r equals 1, then of course you can just see limit n goes to infinity, or 1 to the n, but 1 to the n is just basically 1, so the answer will be simply 1. If r is equal to, for example, negative 1, then we have limit n goes to infinity, negative 1 to the power n. This we know it just doesn't exist. So when it's 1, it's just convergent. It doesn't exist, so this will be divergent. You can see, because if you list the terms, and this is oscillates between negative 1 and 1. So this limit really does not exist when r equals negative 1. So here's just the next part that will be so important to know. This one is just like a fact that can be proved by using, for example, the sequence theorem. But if limit of the absolute value of a n as n goes to infinity, if the absolute values goes to 0, then limit of as n goes to infinity of an must be 0 as well. So this is really a fact that we can employ in this problem. How is just here is the way. I mean, we can just see if -1 is less than r and less than 1, then what do you think about limit of absolute value of r to the power n as n goes to infinity? Now look, if r is between -1 and 1, and if you take like powers of r, then you can just see this will be like r, and then we have just absolute value of r squared and absolute value of r cubed, and it will just continue like this way. But you can see this will just converge to 0. Why? Because absolute value of r is really less than 1. If you multiply it every time by itself, you're making it smaller and smaller. Like an example, for example, small one, limit 1 over 2 to the power n, that really goes to 0. You're just multiplying by itself. So in this case, for example, r is simply 1/2. So this limit, by looking at this way, this limit is just basically 0. So then that really implies that limit of r to the n must be simply just 0 by using the fact. So as n goes to infinity. So we know, like, if r is between -1 and 1, then this limit is simply convergent, and it converges to 0. And then the last case, like if you really have, I mean, you could just see if r is larger than 1, then the limit of r to the n, we can definitely say that goes to infinity. Why? Because it's like r and then r squared and then r cubed and then so on, and you can see this goes to infinity because r is greater than 1. It just gets larger and larger. And if r is less than -1 though, now this time just be careful. If you take limit of r to the n, then this will just, you can see it will kind of like oscillate between the negative values and the positive values. So this time the limit does not exist, but you can just explain by using this way, like the positive values of r, positive values of r to the n will just go to infinity, and the negative values of r to the n will just go to negative infinity. So example, like for example, if you take list -3 to the n, you can just see, as a simple example, it will just be like -3 and then 9, then -27 and then 81 and then so on. You can just see the negatives really go to negative infinity, and the positives really go to positive infinity. So the limit doesn't exist. It's kind of like oscillates between negative and positive large values. So I mean, in conclusion, you can really say that this sequence, like Rn, we can just really write that in here, that Rn is just, this is the limit of Rn is, so we can just do out into 2, and then we can just say it's convergent if -1 is less than r less than or equal 1, and it's divergent otherwise. So this sequence is really an important sequence, especially once we go through the geometric series. That will be important. So thanks for watching, and see you next time.